a presidential award from Obama for engineering and scientists. He also received very recently the most prestigious award from the American SNF, the Waterman Award. So last week, Rob published in Science an article on the first controlled flight of his insect-sized robot, and so there could not be a better time to listen to his current progress in insect-led robotics. Please.
So, thank you, Professor Floriano, and my sincere thanks to the organizers for inviting me here today. So I'm going to be talking to you today about a primary project in my lab called RoboBees, and I'll go over what that means. And if I have time, I'll tell you a few highlights from some of the other activities in the lab. So I'd like to start, though, by first taking an observation of what appears to be a simple maneuver, in this case by a bee. And it starts to sort of think about the questions that this might invoke. So how is this animal moving through the air, moving its wings through the air? How is it generating and manipulating vortices in the air? What are the flight musculature and the thoracic mechanics that are powering the wings as it moves through the air? What are the metabolic processes that are powering flights? What are the sensory modalities that it's using to hover or avoid obstacles or find the next flower? And these are the types of things which we as engineers use to develop very well posed but fantastically difficult engineering challenges that we're aiming to tackle in this RoboBees project. And so these are the types of things we like to build in the RoboBees project. I'll get into more detail, of course, on what they are. Maybe as a high-level overview at first, the RoboBees project is split into three main categories: body, brain, and colony. Body being all things associated with the flight apparatus, brain being controls, sensors, and computation, and colony being coordination. How do you take multiple individuals like this and have them work together? So I'm mostly going to be talking about topics in the body, which is my work, my group is working on. So to sort of orient all of ourselves, of course this is, if we were to say as engineers, let's make a little small thing that flies around like an insect, this is going to be a naturally bio-inspired project. And we take quite a bit of inspiration from flies and bees. I'll sort of use the two in terms of their basic features more or less synonymously. But it's basically two wings, each wing having multiple degrees of freedom, so 3 degrees of freedom per wing, which is this flapping stroke, which defines the flapping plane. A simultaneous rotation about an axis, which is roughly parallel to the span, to the leading edge. And the stroke plane deviation, this sort of out-of-plane motion, allows you to do these sort of figure of eights or U-shaped trajectories. So I'm going to ignore the stroke plane deviation and just say what we're focused on primarily at the beginning of this project was trying to figure out, well, how do we actually manufacture devices which can move their wings with these 2 degrees of freedom at approximately the same scales and wing beat frequencies that you find for insects, for let's say fly or small bee-sized robots. And that brings up a number of interesting engineering challenges. And so I'm going to talk about 4 of them in some depth, and that is design, manufacturing, control, and actuation. And then, time permitting, I'll talk about some of the other topics that we're now moving on to, giving some solutions to these challenges. Okay, so the first one is manufacturing. So the thing that we've been working on for quite some time, and this goes back, I'll give a little bit of the design history later on, but this goes back to some of my graduate work under Ron Fearing at UC Berkeley. First thing to think about is, well, okay, how do you actually build these things? And so they exist, it turns out. If we think about the feature size of these devices being roughly ranging from micrometer to centimeter, that exists on a really interesting scale. And so on the lower end of that sort of size regime, you can think about maybe more silicon or integrated circuit-based micro electromechanical systems, MEMS techniques. And I'm showing an example here, which is what I consider one of the more successful commercial applications of MEMS. This is a surface micro-machined DLP projection system from TI. But it just sort of illustrates the types of devices, some of the small features, sub-micron features you can achieve. This is on the lower end of the things that we're interested in, both in terms of scale. It also, with respect to the things that we want to do, is a little bit too restrictive in terms of the three-dimensional topologies that we can achieve. A little bit restrictive in terms of the materials that we could use, but most importantly for us, given that we know relatively little about the way that the devices that we want to make will operate, the physics of the devices, we need to be able to manufacture these things very, very quickly on the order of hours or maybe days. And so the time constants associated with MEMS are going to be appropriate for us. And then, of course, on a larger scale, so this macro scale, more nuts and bolts approaches. This is sort of illustrating hundreds of components that are assembled into internal combustion engine. You can imagine that if I say, well, I want to build something the size of an insect, I'm not going to be wanting the bolt to be bolted together hundreds of thousands of pieces under a microscope. So it's a really interesting scale regime that we call this mesoscale. And we've been putting a lot of effort into, well, how do we actually manufacture devices very rapidly, very cheaply, with any material that you might want, and with any topology or degrees of freedom that you might want. And the solution that we come up with that I'll get to in a moment is called pop-up poke MEMS. And it's inherently inspired by a few sort of well-known techniques. 3D printing, multi-layer printed circuit board, and bulk machining. And I'll go through that very briefly. So the first two steps here, the first step is bulk machining using a non-contact laser micromachining system. And the nice thing about that is if you use a UV laser, for example, you can basically cut through any material that you want. Ceramics, polymers, metals, composites, doesn't matter. And so we take thin sheets of these materials, we machine them in 2 dimensions. In the second step, we do, this is supposed to be illustrating persistent pin alignment, so which is very similar to manufacturing techniques for multi-layer printed circuit boards. We basically take all of these layers that we have machined using this UV micromachining system, stack them up and bond them together. Now one of the keys, what we call sort of the old way, which is also called graduate student with tweezers, so basically having a tremendous amount of skill and training to operate under a dissection microscope and putting these things together. I don't want to put this down per se because it works. It allowed us to make some progress in these areas. But as you would imagine, it required a tremendous amount of skill. A graduate student would have to come in and basically take years, possibly years to get good at this. The yield was low, have some sort of manufacturing errors, etc. You're going to be extremely conservative in your designs, and so that's going to really slow progress even more. Whereas if it's something you could do in a matter of hours, and you could do things sort of in parallel, where you could make these things, maybe 3, 4, 5 at a time. And it takes inspirations from children's pop-up hooks. And so the inspiration here is you can think about a pop-up hook as developing these fantastically complicated structures, three-dimensional structures, sometimes even mechanisms, by very, very unskilled workers. In this case, I'm referring to the children, not the people who make the books. So we tried to take inspiration from this to actually make some of the components of our devices. So you can imagine that if I want to create a little flapping wing thing that has wings over here, and an actuator over here, and transmission mechanisms over here, as opposed to doing the sort of nuts and bolts under the microscope thing where I sort of bond these things together and do this manually, I can sort of take inspiration from Feynman's little hands, where he was describing robots making robots. And so this is exactly what's going on here, where we build not only the components of the robot into the structure, we also build the structure that's building the robots. And we do this in such a way that all of the assembly trajectories that are required to put the wing over here next to the actuator over here, all of that assembly is built into parallel mechanisms that are built into the thickness of this laminated structure. And so this is based upon the ability to, this comes back to what I was saying, the ability to machine the freestanding pieces. If we do that, then we can connect any layer to any other layer, anywhere we want, to the thickness or to the area of the device, making what we call mechanical vias, which is directly analogous to electrical vias, and allows us to make now not just sort of folding devices as I think about controlling the degrees of freedom of the device as I assemble it. So I get the device after lamination, it's just this rigid body, it has 0 degrees of freedom. I release one of the degrees of freedom, which is the assembly degree of freedom. Then I have this 1 degree of freedom, which defines all of the assembly, and that's what's going to happen here. I basically push on it. In this case, I push on it. I separate 2 plates of Osiris linkage. All of the other assembly trajectories are built into that motion, or coupled to that motion. So I still have this 1 degree of freedom, though. So after I actuate that 1 degree of freedom, I want to lock it into place in the assembled state. So once I do that, then I go back to a rigid body. I have 0 degrees of freedom again. After I do that locking, in this case, this is using just a dip soldering method, which sounds horrible, and it sort of is, but there's other methods to do this as well. Then I can just release the structure away from its assembly scaffold, pluck it out, release the the functional degrees of freedom as well, and now I've got this functional device that I can sort of plug in and turn on. Hopefully, it flies away. So that's how we make these things. I'm just going to show you a few examples of different devices and structures we can make in this way. This drawing here is supposed to illustrate some of the complexity that's built into these structures. So one of the challenges now is not in the actual sort of dexterity required to assemble these devices. It's actually in the design. So this is actually the big bottleneck for us now, is that there's no CAD software which is appropriate for this. So this is one of the things we're currently working on. Here's a device that after it's popped up, false colored in gold and blue to tribute to my alma mater. And this is the device after it's released. So I'll just run through a few examples of other things that you might be able to make. Some of these have absolutely no function other than their artistic value. Some of these are actually interesting robots in and of themselves. So this is a device, this is a structure which is now going to unfold. As opposed to just separating plates, this is going to sort of unfold into a structure, which is a 1/900th scale model of the right wire. There's other things that you can make. You can make interconnected chains of composite materials. We would argue, I'm not sure how else you would do this with fiber-based composite materials, nor can I think we would use for it, but that's okay. We can do things, by the fact that we're doing things in parallel, allows us to sort of mass produce, and for us, mass production means things on the order of 10 made simultaneously. This is just a spherical 5-bar, but it's illustrating that point. People often ask us, well, can we make curved surfaces? And the answer is, well, no, but we can do approximations to curved surfaces by making complex polyhedra. In this case, this is an icosahedron, a 20-sided regular polygon just focused in the middle area that's being popped up in similar ways. We can make self-assembling devices. You can sort of see a spring-like pattern in here. This is just made by having a pre-stressed material within the laminate, and then once that's released, it sort of pops into shape, so you do self-assembly. And like I said, we can make other very interesting robots. This is a robot with my graduate students, Andy Beisch, recently made. I'll show that if I have time. Katie Hoffman has made a centipede-like robot using these techniques. Mike Carpelson has made sensors using some of these techniques, and I'll come back to that in a minute. I should also mention that one of my former students who has actually started a company that's Pratik Sridharan, who's actually trying to commercialize some of these techniques, and so if you want to buy any of these robots, I would encourage you to talk with him. This is one of the things he wants to do. Okay, so now we know how to build things, and now one of the major questions is, well, how do we actuate them? What are the motors that we're going to use? And this is a particularly easy to state that, well, if you don't have enough power in your motors for your flapping wing device, you're simply not going to get off the ground. To put this in perspective, the things that we would use on a larger scale robotics and more ubiquitous electromagnetic motors simply won't scale for a variety of reasons, manufacturing being one, but even if you could build them, the physics of scaling is going to tell you that you're not actually going to be able to get much performance out of them. To illustrate this, the AC induction engine in a Tesla Roadster is something like 7 kilowatts per kilogram at greater than 90% efficiency, whereas the smallest motors that you can buy off the shelf, which are on the order of a couple hundred milligrams, they might be small enough, but they're on the order of 39 watts per kilogram, or 39 watts per kilogram, and around 15% efficiency. So we can look through instead a number of induced strain materials, where induced strain means that we have a very simple change in shape upon the application of an applied stimulus. And so we look through different materials, be they piezoelectric, be they phase-changing materials like shape memory materials, electroactive polymers, be they dielectric or ionic. We compare these across a number of standard metrics, force displacement of the product being work, normalized. And this is manufactured in the exact same way I just showed you for the other devices, where by the converse piezoelectric effect, I want to apply a field across the thickness of one of these plates. It wants to contract. It can't do with boundary conditions, and so it bends. I do that on the other side, it bends the other way. So a very simple oscillating actuator. They have a number of nice aspects and a number of downsides as well. The nice thing is that they scale down very well. So the energy density is very low, a couple joules per kilogram compared to, let's say, shape memory materials that might be a couple kilojoules per kilogram. But the bandwidth is very high. So if I have something small that wants to oscillate, and as I get smaller, my natural frequency is going to increase. So I'm going to start to oscillate faster. Then these things, so long as I'm running them in a quasi-static sense, which I am, then the power density gets very good as you get smaller, on the order of insects or even better. And we use these things in a lot of different robots, and we can mass produce them in the same ways I showed you before. Okay, so that's manufacturing and actuation. Now I'm going to go through a couple of some of the design history and bring you sort of up to date on the types of designs that we have now. So back in the predecessor to RoboBees was a project called the Micromechanical Flying Insect Project. It was run by Ron Fearing. That started in 1998 with a vision very similar to what we have of creating controlled autonomous flight with something the size of an insect. And that progressed. I actually noticed this morning when I was going through my slides that the version of the upper middle there actually looks strikingly similar to the one I'll show you that is actually flying now. It got to the point while I was a graduate student there that we were actually able to figure out some of the manufacturing techniques, figuring out some of these actuator techniques, actually developing structures that could flap their wings in very similar ways as insects. There was a key breakthrough when I got to Harvard that I'll get back to in a minute that sort of launched us for this NSF Expeditions in Computing that we have now called the RoboBees project that I've already described to you. And that brings us more or less at the current date. Now this sort of cute demo that we had back in, this was 2007, 2008, was that we showed that we can take these more complicated designs that we had at Berkeley and sort of scale it down to a single actuator, which is flapping two wings. And the innovation here was that as opposed to commanding the second degree of freedom, we allowed it to be passive. And there's a lot of, actually, it turns out there's a lot of evidence that a lot of insects do this as well. They put most of their effort into flapping their wings and allow the rotation, the pitching motion of the wings to be passive. And so that greatly simplifies things, allows us to do some dynamic decoupling of these two different degrees of freedom, and it makes it easier to manufacture. So we were able to assemble all these things together. A single actuator, these two wings, show that we get thrust greater than weight. So that was a nice demo, but I'm saying it's a cute demo specifically because what it didn't show is the most important things. What it didn't show, you can sort of see, it's sliding up a rail, so it's not controlled. It's got wires dangling, so it's not powered. There's nothing to say anything about the design optimization or the fluid mechanics associated with this. And so this is what launched us on to some of these topics that we're looking at in RoboBees. So I'm just going to highlight two current designs. The first one we call a dual actuator design, which is designed by Kevin Long. And this one is quite simply, you take the previous version that I just showed you that was sliding up the rails, where it only had one actuator is coupled to two wings. Now I take that actuator and split it in half, so that each separate actuator now is half the stiffness, half the weight, half the force, but driving half the load. And so it should be a wash in terms of the overall power to weight of the structure. And now, by independently actuating each wing, we can get not only the thrust to get off the ground, but quite a bit of control authority that I'll show in a moment. This was an image that they had in their science paper. Apparently it took them all day to make this picture, I don't know why. This is sort of showing the operation of the device. This first kind of looks a little bit weird when its wings start actuating independently, but it sort of illustrates the fact that you can independently control these wings. And that turns out to be tremendously important. So this is how you actually get your control authority from this device. So thrust is just modulated by amplitude modulation, higher stroke amplitude, higher velocities, higher thrust. Now, if I want to get roll, for example, quite simply, I flap one wing with a greater stroke amplitude, greater velocity, greater thrust, and the other one I get a roll torque. Pitch is similar, but now I sort of bias my stroke either fore or aft with respect to my center of gravity, and I get a pitching moment fore or aft. Yaw is actually rather tricky, and this was something that was solved by some collaborators at Air Force Research Labs, where they figured out that if you keep the same, you don't want to change the frequency that you're operating at, because we're operating around resonance for stroke amplification reasons. You don't want to change your operating frequency, but if you flap faster on one half cycle and slower on the other half cycle, then you can get an asymmetric drag profile and actually sort of paddle yourself through the air and create a yaw torque in that way. That's called split cycle control, and that actually works pretty well as well too. Okay, so that's one design. A more bio-inspired, if you will, approach is created by Zing Teo, and he's actually going to be talking about that this afternoon in case you want more details, but I'll give a quick highlight. In this one, now is a rather complicated mechanism now. This is actually one of the more complicated things we've ever built, and it shows the complexity of devices we can make. In this case now, you have two actuators. One is just commanding flapping, and another one is asymmetrically coupling a bias on the yaw, on the wing hinge, which I'll show in a second. But the complexity is actually really interesting here, where you actually have two planar 4 bars, two spherical 4 bars, and two spherical 5 bars in something that's less than a centimeter in sort of width. This is what it looks like as it's made. This is how this actually works. So the yaw is actually, it gets to be a little bit easier here. This is actually where it becomes bio-inspired. It's hypothesized that some flies do this as well, where they can actually, as opposed to changing the velocity on upstroke or downstroke, they just bias the angle of attack so that you get different drag, and you can do the same thing for different lift profiles and get different torques to generate roll as well. And this is sort of what it looks like. You can sort of, I'll just step you through here. It might be a little bit hard to see, so I can show you, or Z can show you maybe later this afternoon in case you want to know the operating principle. This is in real time. And if you sort of compare on the left and the right for both of these mechanisms, you can see that there's opposite sort of asymmetries. And same thing for yaw. And it turns out that dynamically, when you operate these things up at high frequencies, around resonant frequency around 110 hertz, this is, you can start to see the sort of asymmetries become even more pronounced and allow you to create roll torques. Okay, so now that's design. So we have multiple designs. I'm not telling you about the other half dozen or so designs that we've worked through over the course of the last few years. But the flight control is the next thing I want to discuss. So we do control, maybe to step back in the RoboBees project in general, we're splitting up these topics into multiple parallel tracks. So sensing, computation, control, the development of the device, design, power, etc. are all happening in parallel. And so we don't want to wait for the perfect power source or sensor to be put on board in order to actually do flight control experiments. So everything I'm going to be talking about is going to be tethered with respect to control instead of power and control. It happens in this sort of arena. This is a motion capture arena that every one of you have seen before, probably most of you have. The same exact cameras, the only difference is that they're a foot apart. So we're talking about working volumes on the order of a cubic foot. And there's the robot, as you can see. And the control architecture itself, I won't get into too much of the details. There's some interesting things in this. Maybe the most important aspect is that the three main control blocks are operating sort of independently, simultaneously. The highest authority is given to the attitude controller, so keeping it upright. And we're talking about now, our goal, I should have said, is hovering. So just keeping it upright is given the highest priority. And the set point for that is determined by a lateral controller, where if I have a set point that I want to be at in space, the further I get away, the further my set point deviates from upright. And then there's an altitude controller, which actually turns out to be the easiest one. Some of these, so we might ask, well, what is the actual control that's being run? And the nice thing about having these devices is that we can play around with whatever controller flavor that you like. We can do things as simple as PID to maybe a little bit more complicated, like adaptive controllers, to try to learn some of the unknown parameters, of which there are many. In the dynamics of the system. Okay, before we start to control any of these devices, we take them, plug them in, and start to do trimming exercises. So this is what these trimming exercises might look like. They're extremely unstable in open loop, so they're going to crash every time, but the idea is, let's see if we can sort of trim and tweak the control inputs to the system to get as sort of, that would be considered a very good one, as sort of straight and open loop flight as we can, and then do control around that operating point. Here's actually what this looks like in real time. So when it doesn't work, it's very uninspiring. But when the controller does work, and this was what's got this so excited recently, you can just sit there and hover indefinitely. And so this is at 1/8 actual time. A couple things you can sort of see that are going on here. These little retroreflective markers that are being seen by the Vicon system. It's flapping at 120 times a second. There's the control moments, because the moments of inertia here are so small, the control is very subtle. It's actually very hard to see what you're doing. You have to actually look back at the history of the inputs to actually get a sense of what the controller is actually doing. But these things will just sit there and hover indefinitely. One of the questions you might have is lifetime, which is actually quite an important consideration for us. I can come back to later. We can now do seemingly simple things like lateral maneuvers. So this is just changing around trajectories and changing around set points in space. You can fly around. Again, this is at 1/8 actual speed. And you can sort of just do this as much as you like. These are all the same. I think all the videos I'm showing you are from the same device. The devices typically last on the order of tens of minutes of flying time, which is actually kind of long if you consider the fact that they're operating over 100 hertz. So on the order of many tens of thousands, if not hundreds of thousands of cycles. never break the same way twice, so I can't answer I can't tell you what is the exact failure. So this will just continue to do this indefinitely. This is what it looks like actually in real time. And I encourage you to check out some of the videos on our website now that actually have the audio from this too. It sounds annoyingly like an actual insect. We can also do takeoff and landing. This is, again, slowed down quite a bit. It's probably very hard to see here, but this is playing around with a landing gear as well, with another set of studies that we're doing on how to actually design the systems. This is an example of how we think about designing the systems, actually make control a little bit easier. We don't want to have perfect control because of all sorts of things that happen when you try to land and ground effect and in this case the wire and all of that. And so we actually put some effort into designing landing gear as well. And we'll just sort of sit down in a second. I think. Great. Okay, so that's manufacturing, actuation, design, control. And I just want to come up back and highlight just a few other topics which are going to be important for bringing this to full autonomy. So this is where we are today. A lot of what I'm going to tell you about now is sort of ongoing and future work, but it's going to be addressing some of the remaining key challenges to bring the RoboBees project to fruition, and that is understanding the fluid mechanics. I haven't really said much about that yet. Understanding computation, power, and sensing. So first is fluid mechanics, and this is just going to be sort of motivating why this is an interesting problem to us. Now, keep it in your mind, we're not fluid mechanicians, we're roboticists that can make very small things that sort of flap like an insect. But we want to sort of answer questions, we'd like to answer questions like structure-function relationships, either in natural systems, and we work with biologists to assist us with this, but maybe more practically is, well, very simply stated, how do we design a better wing for the RoboBees? And structure-function relationships and fluid mechanics of these devices, in fact, it's quite the opposite. We have the nonlinear time-varying second-order PDE. That's not going to really be quite useful to us, not being CIT people. And so what people tend to do is take an approximation to this, where you hide some of the unsteady terms, you hide some of these nonlinearities behind force coefficients, and then try to use either experiments. Use this apparatus that we've developed where this looks rather complicated, but it's basically just a wing drive mechanism where we can flap wings, we can measure the resulting lift and drag that the wings are being generated. We can set up high-speed video cameras to watch the motion of the wings. We can set this whole thing in a vacuum in case we want to suck all the air out and do inertial tears. And this is sort of what it looks like if you peer through. This is sort of what it looks like from the perspective of the high-speed cameras. This is operating, again, I think around 100 hertz. Extracting out motions, you can extract out forces. And the idea is the following, and this is sort of just a vision of the future. This is very much an active project in our lab, where you have a set of inputs which might be wing shape, maybe aspect ratio or area distribution, how compliant or rigid the wing is in properties of the wing hinge. And we start to measure things like, well, the relationships between the stroke angle and the hinge angle, and try to fit models to where the center of pressure on the wing is, and actually eventually trying to characterize performance of the wing in terms of lift or lift power or whatever measure you might want. So this is very much a work in progress. So one of the questions we often get is power, of course. This is just sort of a generic overview of the architecture of the electrical architecture of the RoboBee as we see it. You have perhaps multiple power actuators, perhaps multiple control actuators. There's a brain integrated circuit, I'll come back to in a moment. In the middle, there's a power integrated circuit, which is doing, I'll describe in a second, is doing all of the sort of boost conversion to take the source voltage and condition it properly to control the actuators. Some magnetic components. We can take the only takeaway from this slide is we can take this architecture and take our best models of all of the individual components, combine them together, do a little bit of an optimization study, and get things like mass and power budgets, and that's what you're seeing here. Now, the details might not be terribly interesting, but what is sort of interesting to note is that the mass budget is dominated by two things, the power actuators and the battery, and that's just due simply to how energetically expensive it is to fly at these small scales. If you look over the power budget, it's all actuators. It's all trying to get off the ground. And I'll say just one quick slide on the power architecture itself. There's really three key elements. There's the power source, and so for the power source, we are looking into a number of different options. So batteries, the batteries actually, existing lithium polymer batteries actually have energy densities and discharge capabilities which would power flight for a few minutes if they existed on the proper scales. They don't. And so we're going through the sort of painstaking task of cutting these things apart and repackaging them smaller. that's sort of the low risk, low reward sort of approach. We're also working with a group at the University of Washington to do wireless power, and we are working with material scientists at Harvard to do microfuel cells. Once you have a power source, you still have to condition that power. You have to boost it up to the required drive voltages for these voltage-driven piezoelectric actuators. And so that's done with this integrated circuits here, which is just a custom integrated, high voltage integrated circuit that's effectively coupled with these magnetic components as a tapped inductor boost converter auto transformer circuit. Okay, so all of these exist in some form and are being sort of slowly migrated on board the RoboBees. I'll say very quickly that the computation, of course, you're not going to be able to put on anything off the shelf. Is not going to work for computation. So instead, what we're going to do is develop custom integrated circuits. This is being done by collaborators Leon Lee and David Brooks, who are VLSI experts at Harvard. We're actually manufacturing integrated circuits to do all of the computation of the brain. The architecture looks something like this. Their key innovation here is that they have. It's not a general purpose computation. There is a general purpose core, it's an ARM core, but it has a number of little specialized blocks, which are they call accelerators, which basically do one thing and do one thing very well. So process optical flow information, do some of these control algorithms. And they have a process by which we can as the engineers that are doing the control, we can take our algorithms, just basically give them C code that describes an image interpolation algorithm or whatever the control algorithm that we're using, and they have a way to compile that down into silicon. And they're actually manufacturing the second version of these integrated circuits right now. So I'm out of time. I'll just highlight some, in the last two slides, I'll highlight some sensor work. First is optical flow. We're working with a guy named Jeff Barrows, who has a small company called Sentai. This is now an old example, but it's the first example of actually bringing sensing on board the Bee. In this case, this is an optical flow sensor, a 1D optical flow sensor on a device which is constrained, but it's controlled such that it's going to be doing station keeping relative to a moving background. So this tells us that we can actually start to integrate power on board, and we're actually working on an omnidirectional version of these sensors with Jeff. There's a number of other sensors I won't have time to get into that we are also working on. This is perhaps the only instance where there might be some off-the-shelf components, mostly due to miniaturization for mobile devices. So I guess I'm probably out of time. 1 minute? Okay, I'll go on. 1 minute I'll go through. So RoboBees is about half of what my lab does, so in 1 minute I'll give you some highlights of some of the other things that we're working on. Other designs for taking some of the same manufacturing processes and looking into other forms of locomotion. So this is many-legged locomotion inspired by centipedes. And again, not just to make the robots, but actually to study things like how passive undulation modes in these severely underactuated systems can arise and lead to interesting locomotion capabilities or enhance the cost of transport, for example. We can make, and this is an example of one of the first fully pop-up devices that we can make, is a small, in this case, quadrant head. This is, the upper one is in real time, the bottom one is showing locomotion, which actually is operating relatively fast. It's operating on the order of half a meter per second, which is over 10 body meters per second, which is actually pretty fast. We have a project in the past which is sort of harkens back to assembly by folding, which was a project with Ron Fearing and Vijay Kumar and Daniela Roos to do programmable matter. This was a way of doing programmable matter by folding, making reconfigurable robots that were basically sheets of this composite paper that would fold themselves into multiple objects. In this case, it was a boat and a little simple paper plane. We also started to get into some soft robots. I won't have time to get into the details of this, but it's based upon these are two examples of hyperelastic strain, pressure, curvature, shear sensors that you can stretch to many times their original size and still remain functional. This is based upon a combination of microfluidics and a room temperature liquid metal. And you can, these videos will show all sorts of functionalities, measuring in-plane shear forces, normal pressures. You can stretch and basically make strain sensors out of them. We've applied these and other technologies to soft wearable robots. I won't have time to get into this. This is now being spearheaded by a much larger project by Connor Walsh at Harvard. So I'll skip that. And there's a number of other projects. I think I should end there. Thank my sponsors. Thank you all, of course, for your attention. I want to give a couple of important plugs. One of the plugs, of course, is is robotics at Harvard. So this is something that we're trying to build up, and my personal goal is to make Harvard one of the premier places for robotics. And of course, all of the students and postdocs who have made all of this work possible. Many of these faces are in the audience, and a number of them have started their own labs that I'm very proud of. So with that, I'll stop and take any questions.
Fantastic talk. So we can take now a few questions. We have 7 minutes left. Any questions? Is there one there to talk to? Here in the
Thank you very much. The question is good from Nagoya. Thank you very much for such an excellent talk. Okay, but can you tell more about such a kind of optimal design, sort of like a scale factors in terms of such a kind of such a flat scale versus such a kind of actuation power? I do see such a kind of reason why such a 3 centimeters and so like that. There is some other factors. Maybe we can take it account. Yes.
Yeah.
Please.
Yeah. So the question is a great question. Thank you on optimal design and scaling laws that are associated with components, considered components. Why is the thing the size that it is? Well, there's really interesting. I can't tell you where the breakpoints are, but there's regimes where you want to do things like we're doing with respect to small oscillating actuators and flexure-based joints, and then there's regimes on the larger end where you want to, the actuators would break down. They wouldn't work. Their energy density would be too low. The operating frequencies would be too low. I can't tell you exactly where they are. We've done some studies which suggest that it's on the order of gram-sized devices, where below that, you're probably going to want to operate with some sort of oscillating, actuator, maybe piezoelectric would work fine. But above that, your rooming frequency is going to start to slow. So a number of questions arise, which I'm not sure I have a satisfying answer for. You can do flapping units at those scales, in larger scales. Probably not above a certain size. Do you want to switch? At what point do you switch to motors as your primary actuation mechanism? So I would argue it's on the order of something on the order of a gram, but I can't really back that up. The reason we're operating on these small scales is because you can't use these other things. And what really drives us is the sort of using the scale as a motivation for some of these technological challenges that we have to overcome. So there's not really a good reason why we're this small.